I believe more students will be joining, so let them join. We can start. So yesterday we discussed about the viscous incompressible flow. We discussed about the viscous incompressible flow. Typically, flow between two parallel plates. Both the plates are stationary. Now, the exercise that actually we discussed was basically the application of Navier-Stokes equation. And if you went through this note as well as the video lecture, there was another approach, the conventional approach of control volume, that was also done. So those I think you can go through. Just a minute. Devojit Das. Okay. So that part we already discussed. Now the second part. Okay, before going into that, I mean, extension of the situation of flow through two parallel plates is what we call as coed flow. In that case, one plate is moving with respect to other, or in other words, we can say plate is having relative velocity. Steady, of course, there is constant velocity. That is what we call as coed flow. So for that situation, how we can model the situation, mathematical model. Again, here if we look into the Navier-Stokes equation, it is basically the same application. Just one thing that changes is the boundary condition. If you look into the flow through parallel plates where both the plates are stationary, referring back to this figure once again, here you can see at y equals to 0 as well as at y equals to b, the velocity u is equals to 0. Okay. Here. So when we are going for the evaluation of the two constants, C1 and C2, which actually arises due to the integration, we had a double integration. So indefinite integration, and due to that, there are two constants, C1 and C2. So we need to evaluate these two constants, and the boundary conditions are essential here to find out the constant. So one can notice that these are the two boundary conditions. At y equals to 0, we have u0, and y equals to b, we have u0, because of this no slip condition. All right. So from that, if you use these two boundary conditions at equation 4 and 5, we get both C2, actually 5 we have done. So boundary condition in 5 and boundary condition 2 in, again, the same equation. If you use, you get the value of C2 and C1. And that actually led us the expression of u, that is the velocity profile, we can say, in this manner as it is depicted in equation 6. You can see. Now, for coed flow, what changes take place actually? It is almost, same thing, the same exercise. The only difference is that the boundary condition. So here you can notice that at y equals to 0, Just a minute, okay?
Okay.
Okay. So here one can notice that the change that actually takes place is in the condition at the boundary. Because one plate is moving with respect to other at a velocity, constant velocity up, we have at y equals to b, as per the reference frame we have chosen. At y equals to b, we are having u is equal to up instead of u equals to 0 by no slip condition. Again, here also we are applying the no slip condition, due to which we are having u, that is the velocity of the fluid, which is attached with this plate, moving plate. So by no slip condition once again, we are having u equals to up. So these two conditions once again are from no slip condition. At y equals to 0, that is at the plate which is stationary, or if you fix the coordinate frame with this particular plate, which may have a velocity, but if you fix it, if you fix the reference frame with this plate, then it will be 0 velocity, and with respect to this plate, if the other plate is moving at a velocity up. So that is even if it is 0, I mean, even if the stationary plate or moving plate, the bottom one, it doesn't matter. Always you can have y at y equals to 0, velocity equals to 0. But the condition is that you need to fix your coordinate frame with the bottom plate. So this is the change, and accordingly, what happens actually, you get an additional term in the expression of up, or u, not up actually, it is u. So if you look into this part, I think this part, typically, here you can compare between the one for flow through parallel plates and this one, which is the expression for quiet flow. Basically, what I mean to say, this term is common. This term was there in your previous expression of velocity. This is the additional term actually, up into y by b. It is basically a linear term. One can observe y by b, where y is the variable. So, and up and b both are constant. So it is a kind of mx, y equals to mx form. So a linear term is being added with a parabolic or a quadratic term, which was there earlier. So that is the difference we have if you are having a change in the condition, and accordingly the the expression gets changed, but the treatment remains same. So it is the same treatment that has been done to find out the velocity profile. And if you want, you can proceed further to find out your q, which again, which will be equals to, we need to integrate from 0 to b once again, and it will be u. Then what you need to write? I have written u. What else I need to write?
DA.
DA. What is DA? Yeah, DA. So what is your DA? DA is equal to what? You are having a consider. You need to consider a plate. I mean,
Yes, sir.
2 pi r dr.
Yes,
Yeah?
sir. Sir, 2 pi r into dr. 2 pi r into
No, এটা প্যারালাল প্লেট এটা
2 pi r.
sorry, এটা প্যারালাল স্যার, আমরা নি ওটা রাউন্ড শেপ ভাবছিলাম, সরি ওটা।
Yeah. So it will be
w into dy আর কি।
W
again,
W টা যদি উইক
dy.
হয় আর y টা যদি ওই
Right.
ইয়েটা হয়, হ্যাঁ।
W into dy. This will be your dA. So that you can write here you W dy. So then you need to replace this u by the expression just you can see it, equation 13, and you get the final form of q. Okay, once you get q, you can find out u average, that is q over the area, for entire cross section area. So it is actually, you can write as 0 to b w dy. You can also find out, I mean, from equation 13, you can find out your max. Okay. Using the same treatment for flow through parallel plates. Here the situation is that, I mean, it may so happen one plate is moving in opposite direction with respect to the other. Okay, there are three possibilities. One plate is stationary, the other one is moving. One plate is moving at a velocity less than the velocity of the upper one, but in the same direction. And the third option could be the bottom plate is moving at a velocity other than the velocity of the upper plate and in opposite direction. Okay, whatever be the case, the moment you are having a relative condition, I mean, the treatment remains same. Okay, and also you may have a difference in expression in some textbook or in some other notes. That depends on how you are choosing your reference frame as well as this B. I mean, typically for the case of flow through parallel plates, if you fix the reference frame at the exactly at the middle layer or at the axis, you can see the x-axis is placed at the middle of the two plates, and you can have the distance b and b up, I mean above x in the positive y direction. You can choose one b, and below x, that is in the negative y direction, another. Basically this type of a situation. And so if this is the plate, the two plates, okay, there are derivations in this manner. So this can be chosen as b, and this also is b, equidistant. Okay, and this is your y, this is your x direction. So the moment you do in this manner, I mean, first of all, your boundary condition will change, because here at y equals to 0, you do not you have your velocity 0. So you cannot write at y equals to 0, u equals to 0, something like that. So be careful about that. I mean, the end result remains same if you do the exercise properly. But otherwise, you may end up with a different result, and you may say, sir, this is coming if I do this, this is coming if I do that. That should not be, because the phenomenon, the physical phenomenon remains same. It is up to the, I mean, the person who is doing the analysis, the choice of this reference frame, etc., is subjective. So wherever you choose your reference frame, the end result should not change. So this has to be taken into, I mean, account. I mean, you should take a note of that, the moment you change your reference frame, accordingly the boundary conditions should be written in a different manner, which should be valid for that particular choice of reference frame. Okay, then you will find that even the expression may have a difference, but the result will remain same, because here it is actually 2b which in the case, the way we have written it, it is B. So here 2B is our B. So that is the thing. Okay. But the actual dimension, maybe say this is 0.1 millimeter. Okay. So for your case, 2B equals to 0.1. For my case, B equals to 0.1. That's the thing. Okay, but 0.1 remains 0.1. So this is the way for which you can find that quiet flow. For quiet flow, we are having the velocity profiles as a, composition of linear term and quadratic term. So then actually we have the Hagen-Poiseuille flow, which I think is familiar to you because you had your pipe flow. In fluid mechanics 1. But the only difference here is the treatment once again. Here it is basically the Navier-Stokes equation which we applied. And just you can check whether, or you can decide, which one is convenient. At times, application of Navier-Stokes equations may not give you convenience in comparison to the approach of control volume. Because of that, actually, in our fluid mechanics 2 course, we will be using both the approaches. Sometimes we will be using the application of Navier-Stokes equation direct, we will apply directly. And at times we will also use the control volume approach because that will be more convenient. There is no as such a hard and fast rule that you need to follow this Navier-Stokes equation always. Sometimes control volume approach becomes cumbersome. So, it is actually the choice of, once again, the person who is handling the situation. Okay, so I think this part you should, okay, here one particular difference is that as it's a pipe flow that is axisymmetric, or we are having a rotational symmetry, that is one of the assumptions, as you can see. And the other assumptions remains the same, that is fully developed flow. So the additional part is this is a axisymmetric flow. And thereby we are having, other than the Z or the axial component, that is basically this Z axis is the axial direction, we can say, or this is the axis along which the flow is occurring, which is fully developed. Apart from this component of velocity, that is Vz, Vr and V theta is equal to 0. And this nomenclature you can see is different than the previous treatment that we had in case of flow through parallel plates. It was actually in Cartesian reference frame. This one, for pipe flow, it is more convenient to adopt cylindrical reference frame instead of Cartesian reference frame. That is why actually here also we are having the 3 components of velocity vector, but those are axial component, radial component Vr, and the tangential component V theta. Okay. So these are the difference one may notice for the treatment of pipe flow, that is for the Hagen-Poiseuille equation or Hagen-Poiseuille flow. It is laminar fully developed. That is the most important assumption, or you can say validity of the Hagen-Poiseuille equation. Other than laminar fully developed flow, you cannot use these equations. And also here it should be axisymmetric. That means there should not be any other component of velocity, Vr or V theta. So Here we need to apply the continuity equation in cylindrical reference frame for incompressible flow, and this is the form. I think one can do the necessary coordinate transformation from a linear, that is Cartesian, to cylindrical, and you can get this form. That I think is left to you. You can do better in this type of mathematical transformations. Okay, so I have directly taken the form of this cylindrical continuity equation in cylindrical frame, and putting the term which does not exist, like del V or del R, as VR is equal to 0, so there won't be any kind of this gradient. And the second term as well, as and the third term, that is del V theta del theta. Again, as V theta equals to 0, we do not have this term. So we are left with only del Vz del Z equals to 0. That means Vz is not at all a function of Z, rather but it could be a function of R and T. As because of axisymmetry, any property with respect to
প্রেজেন্টেশনটা অফ হয়ে গেছে
আগো কি হয়েছে
স্যার প্রেজেন্টেশনটা অফ হয়ে গেছে আপনি আরেকবার প্রেজেন্ট করুন
ও আমি বেরিয়ে গেছি দাঁড়া আরেকবার ঢুকি কোথা থেকে অফ হয়ে গেলাম Yeah, the other device actually gets disconnected. Let me join 1 second. Just a minute. আর একটা ডিভাইসে তো কল শুনতে পাচ্ছ তো তোমরা নিশ্চয়ই হ্যালো
হ্যাঁ স্যার কি হয়েছে বলুন
বলছে এই কথা শুনতে পাচ্ছ তো
yes sir you're audible
I'm audible but not the presentation is not visible. Let me
yes sir
স্ক্রিন কি শেয়ার হয়েছে
না এখনো হয়নি
না স্যার
স্যার এখনো হয়নি
না স্যার
এবার হচ্ছে
এবার হয়েছে স্যার
এবার হয়েছে
কিন্তু স্ক্রিন তো কিছু দেখতে পাচ্ছি না আমি তোমরা কি দেখতে পাচ্ছ
না আপনার আইকনটাই দেখতে
হ্যাঁ এবার আসছে
নোটটা ভিজিবল
একটু ল্যাগ আছে মনে হচ্ছে তো এনিওয়ে আমরা কোথায় তোমরা হারিয়ে গিয়েছিলে সেটা বলো
আপনি টার্মগুলো এলিমিনেট করলেন
ও আচ্ছা হ্যাঁ এটা ডিসকাস হয়েছে সো বেসিক্যালি uh, because of VR, that is the radial component, there is no radial component of velocity. The first two terms are eliminated, and due to axisymmetry as well as with v theta, there is the tangential component is 0. The third term also won't be there. So we are left with only del Vz del Z is equal to 0, and that actually implies that Vz, that is the axial velocity, is not a function of Z at all. That is typically the case for fully developed flow. So but it could be a function of R and T. Why not theta? Because once again, as due to axisymmetry, any quantity is not going to be a function of theta. Any quantity, I mean del theta of anything is equal to 0 if you consider rotational symmetry or axisymmetry. Okay, so that is why Vz could be a function of Z, I mean R and T. But again, the moment you are going to consider the flow to be steady, so Vz will only become a function of R, right? So that if you invoke this Navier-Stokes equation, the jet component first, I have done. Because this actually leads going to give us the main equation for this Incompressible flow or pipe flow. Okay, so if you look into this, if you have this VR equals to 0, V theta equals to 0, and also del Vz del Z equals to 0, and here it is written del theta of any quantity is equal to 0 because of axisymmetry. Ultimately, so here you can see, and there is no body force term, of course, if the axis is horizontal. So that is another important condition. So if the axis is horizontal, or we can say the pipe is horizontal, then this body force term, that is rho Fz, this is the body force term. This term won't be there. But it is not the case maybe for any situation. You may have a pipe which is some inclination with horizontal. You may have a pipe which is completely vertical. So in those cases, your body force term rho Fz may not be equal to 0. So you may include it within the pressure term P, and by expressing P as P star. I don't know if you can recall it. P star is the piezometric pressure. Okay, and what is it? That is basically your pressure that includes the gravity term, or rho g h or rho g z, whatever you say, this term P plus rho g z. This complete term is basically the piezometric pressure, and the corresponding head is known as piezometric head. Okay. I think you are aware of this piezometric pressuring. You learned it back to your fluid statics. In fluid statics, actually, this concept are being taught. Okay. So in that manner, you can handle this body force, or else you can just keep it as it is, and then finally you need to do the treatment accordingly. Okay, so basically this is the body force term, which will be 0 for horizontal pipe. Apart from that, we have this del P del Z, which will be there. If you start from the left-hand side, first term for steady state, this will go. This term will be 0. Then the second term, del Vz del R. This, I think, this will be there. Del Vz del R will be there, but what about this VR? As VR is equals to 0, this product will be equal to 0. Okay, so you have to decide by looking at the terms, and accordingly you need to set it either 0 or you need to keep it. The next term also, as this is V theta as well as del theta of Vz, this will be again equal to 0. And then del Vz del Z, even if Vz is not I mean it is a non-zero value, but del Vz del Z is equal to 0. As just before, you have seen that from continuity equation, we obtained that as equals to 0. So in the left-hand side of the Navier-Stokes equation in Z direction, we are having all the terms equals to 0, isn't it? And in the right-hand side, the body force term, if you consider horizontal pipe or the axis horizontal, this will also go. We are not sure about this term del P del Z. And looking into the viscous term, that is this bracketed term, 1 by 1, if you look, here the first one, that is 1 by R del R of R del Vz del R. This term, I think it needs to be retained because Vz would be a function of R. So del Vz del R may be there. But the second term, del 2 Vz del theta 2, again, as it is the derivative, partial differential of theta, would be, I mean, it is the higher order derivative. So, I mean, the first order derivative is 0, so there is no question of having the second order derivative of theta. And the third term also, it is del 2 Vz del Z2, so that should be also equal to 0. So actually we are left with, in this equation, this term and the pressure gradient term in Z direction. So that is why for writing these conditions, we can write the above equation in this form. As you can see, rearranging, of course, by bringing this del P del Z in the left hand side to have it in equation form. So in a similar manner, if you do the treatment with the other two directions, that is R component and theta component of these Navier-Stokes equations, you can see that only apart from this del P del R and 1 by R del P del theta, everything goes out, cancelled out as 0 because of different reasons. Okay, so that I mean from these two equations, 15C and 15D, we can see that apart from R, I mean apart from Z actually, not R. Here from 15C we can see that del P del R is equal to 0 and 15D gives us del P del theta equals to 0. Actually, by again axis symmetry condition, it is you need not use this Navier-Stokes equation theta direction. Straight away, by that condition which we have written here, del theta of any quantity is 0, so P is, that is also another quantity, so del P del theta will be equal to 0. That is actually, you can say, being ratified by this theta component of Navier-Stokes equation. Okay, so ultimately from these conditions we arrive that P is not at all, or the static pressure is not at all a function of R and theta. It is basically a function of Z only. So that you can write instead of del P del Z, you can instead write it as exact differential dP dZ. In a similar manner as Vz is a function of R only, we can also write instead of del Vz del R, dVz dR. So this becomes the form quite similar to the form we have written for flow through parallel plates, where In that equation also we have the two terms involved in left hand side and right hand side, which are function of two different independent variables. Okay. In case of flow through parallel plates, it was y and x, right? Isn't it? You have del u del y or du dy in one side, and other side it was dp dx term, right? So here also in one side we are having function of r, and the other side we are having function of z. So you can integrate it again. You need to integrate twice. As you can see, it is actually double derivative of r, so that you get again these two unknown constants u1 and c2, which needs to be evaluated by imposing the boundary conditions. So the same routine exercise, you can say. The boundary conditions you have to know, and for the chosen situation, here you can see what we have chosen. Again, coming back to this figure, to look into this, at the axis actually we put our reference frame. So that means that r equals to 0, you are not going to have Vz equals to 0. Okay. Vz will have some non-zero finite value, but at r equals to capital R, where capital R is the radius of the pipe, there by your this no-slip condition, we can write the velocity to be equals to 0, which is written at condition 2. Okay. So from this boundary condition 1 at r equals to 0, if you look into the nature of the equation, yeah, we can write this C1 equals to 0 by this equation actually, by this equation at r equals to 0. If you put r equals to 0, you can see that apart from C1, all other terms gets equals to 0, whatever be the value of Vz or dp dz. So without knowing your Vz value at r equals to 0, we can evaluate C1. Because of the very nature of this equation, it gets equals to 0. The condition 2 gives us the value of C2, which is written here. If you put C2 in this equation, the second one here, if you put Vz equals to 0 and r equals to capital R, you get this one, the value of C2. So here you get this value of Vz. Okay, now I think looking into this expression, Vz equals to 1 by 4 mu dp dz, then r square minus capital R square. Looking into this equation, what should be the value of Vz max? If I want to write, if I want to find out Vz max, okay, I need to put r equals to 0, isn't it? That will give me the maximum value. Okay, and that will be minus 1 by 4 mu dp dz r square. Right?
Yes, sir.
So my question is, from this particular treatment leaves us the expression of the velocity, maximum velocity, which is negative. Anybody can explain why this negative term is coming, and whether at all, this velocity will be negative because my positive direction is this one. This is my positive z direction, and this is my r direction. So
স্যার প্রেশার এই ভেলোসিটিটা ডান দিকে হতে গেলে তো মানে বাঁ দিক থেকে ঠেলতে হবে জিনিসটা, মানে বাঁ দিকে প্রেশারটা বেশি ডান দিকে কম, তো গ্রেডিয়েন্টটা নেগেটিভ, সো মানে নেগেটিভ ইন্টু নেগেটিভ পজিটিভ হয়ে যাবে, তো তাই জন্য
yes, that means this dp/dz term is actually, you will get this as negative. It will come as negative. So essentially, the moment it comes as negative, you have the Vz positive value. I mean, the maximum is positive and the minimum value will be 0. It is not going to come as a negative value. Okay, so that is the reason, correctly said. Okay, so this is the situation. Okay, it is already written here. Okay, anyway, so then again you can find out the discharge of the flow rate Q by integrating from 0 to capital R. So that is the limit of the integration, and here the strip of the elemental area or your dA is basically pi r dr. So this is actually your dA. It is VR dA is my discharge, which is written a little bit of in an arranged manner. So we're not this routine exercise. If you can check, you can see that Q is coming as this, and in terms of diameter, if you want to write it, you just write d by 2, so it will be d to the power 4 over 128 mu, and that is basically the Hagen-Poiseuille equation. In radius term, it will be this one, and in terms of diameter, it was like that. So if you are having a pipe of length L, and at the two end, I mean the two end means, say you are having two pressure tappings at point 1 and point 2. So if this is a pipe, and this is the axis, and you are having say here one pressure tapping, here another pressure tapping. This is 1 and this is 2, and this is the direction of flow, where this length is known to you. So if you can able to find out P1 and P2, in this particular form, whatever we have written, here you need to write the pressure drop, delta P, as P2 minus P1, not P1 minus P2, because P2 minus P1 you will get negative. So using that equation, here actually you can see some negative term is coming, minus term is coming in the expression of Q. So if you put P1 minus P2 as delta P, you may end up having the flow rate negative. Okay, so here actually it is P2 minus P1, that is the delta P. If you use this convention of the derivation that is being used here, so your dpdz actually will be equals to P2 minus P1 by L, where L is your
স্যার এখানে প্রেশার ডিস্ট্রিবিউশনটা আর কি মানে লিনিয়ার নেওয়া হচ্ছে কেন, মানে ডিপিজিজেরটা তো অন্য
pressure distribute, এখানে বেসিক্যালি লিনিয়ার ধরা হচ্ছে, ঠিক লিনিয়ার ধরা হচ্ছে, তার কারণ P is a linear function of Z only, as you can see. ঠিক আছে,
পি তো স্যার ফাংশন অফ জেড, মানে লিনিয়ার তো বলা নেই এখনো কথা।
না লিনিয়ার বলা নেই, ঠিকই লিনিয়ার বলা নেই, কিন্তু এখানে
আচ্ছা ক্যালকুলেশনের সুবিধা
ক্যালকুলেশনের সিম্পলিফিকেশনের জন্য মনে হয়
সিম্পলিফিকেশনের জন্য মনে হচ্ছে লিনিয়ার
Not exactly, not exactly. Say, for example, এখানে যদি if you say, for example, if I write Darcy's equation, HF equals to F L by D, V square by 2G. This HF, what is this HF? HF is the head loss. I mean, HF 1 or 2 যে দুটো পয়েন্ট আমি বলতে দুটো সেকশন we have considered. The length is L, the diameter of the pipe is D, and the velocity is the average velocity. So here, if I write it as delta P term, in terms of delta P, if I need to multiply rho G, if I multiply rho G, both sides, rho G HF, that is actually my delta P, we can say. So it will be rho F L by D, right? G থাকবে rho G F L by D square by 2G. কেটে যাবে. So here you can see this delta P is a function of V, that is the velocity, in square, isn't it?
সেই এইচএফ টা কি বললে
But,
বলবেন?
এই জায়গাটা
এইচএফ টা কি আর কি?
Can't you recall this equation? What is this equation I have written? HF is equal to FL by D V square by 2G. What is this equation?
স্যার এটা তো লস স্যার লস স্যার এটা
কি loss এটা?
হেড লস
Head loss. Head loss due to what?
স্যার ফ্রিকশনের জন্য
Friction এর জন্য. What is this equation? এই ইকুয়েশনটার নাম কি?
স্যার ওই তো ডার্সি ইকুয়েশন
Darcy's equation. Okay, তো এখানে আমি এই 1 থেকে 2 তে এই যে ছবিটা এখানে 1 থেকে 2 তে ফ্লোটা যে হচ্ছে তার জন্য বেসিক্যালি আমার এখানে একটা স্ট্রেট পাইপ, তো প্রেসার কেন ফল করছে 1 থেকে 2 তে? Why you are having P2 not equals to P1? You are having actually P1 greater than P2. Why?
স্যার ওই লসের জন্যই
Because of the loss. What kind of loss you can expect here? The friction loss only.
Yes, sir.
Other than friction loss, there is no other loss because it is a straight parallel pipe, right? No bend, no expansion, no contraction, nothing. This is a straight pipe. So the only possible loss is your pressure drop, loss due to friction. So that loss due to friction actually results drop in pressure. So we are trying to look into the situation why actually it is being linear, as it is written like that. So here, if we go through by this loss term, that is the frictional loss HF, and using Darcy's equation, we can write this head loss in terms of pressure drop, because HF is in terms of length, that is in terms of head, that is the length scale. If you multiply with the specific weight or rho G, you get it in pressure form. And that is actually the drop, pressure drop delta P. So we are writing in that way. So delta P, that is actually my P2 minus P1. Right? Convinced?
স্যার
ইয়েস স্যার।
স্যার
Ah.
স্যার আমরা যে ফার্স্ট ইকুয়েশনটা পাচ্ছি নেভিয়ার স্টোকস থেকে, মানে ডিপি বাই ডিজেড আর ভিজেড আর ডিআর এর যে একটা ডিফারেন্সিয়াল ইকুয়েশন পাচ্ছি,
হ্যাঁ
স্যার সেখানে স্যার যদি পি তো শুধু একটা জেড এর ফাংশন আর ভিজেড শুধু একটা আর এর ফাংশন, তাহলে যদি মানে দুজনকে ইকুয়াল হতে হয় তাহলে তো মানে ডিপি বাই ডিজেড কে লিনিয়ারই হতে হবে, মানে দুদিকই কনস্ট্যান্ট হতে হবে, কারণ একদিকে
সেটা
আর
তো
এর
প্রথমেই বললাম, সেটা তো
ওই জন্য তো স্যার মানে পি একটা লিনিয়ার হওয়া উচিত জেড এর সাথে।
স্টেডি স্টেটে তাই তো হওয়া উচিত, তো সেটা তো
হ্যাঁ হ্যাঁ মানে স্যার
এটা তো একটা লজিক। আর একটা লজিক যেটা আমি বলছি সেটা দিয়েও তুমি দেখাতে পারো, ইউ ক্যান অলসো শো দ্যাট,
হেড লস দিয়ে, হ্যাঁ
হ্যাঁ, by this method also you can also show that yes, dp dz is a linear one for steady condition, of course, because the moment you are having a steady condition, the average velocity is constant. So del p by l যদি লেখো, the right hand side কি পড়ে থাকে, del l টা যদি এদিকে চলে আসে left hand side, it comes to the denominator, and the right hand side you are having f, which is the fixed factor, you are having d for a pipe, which is constant, and the velocity is a constant term, g is a constant if you are not changing your place, so everything is constant. So del p by l is a constant term, and if you consider del p by l as dp dz, so that is actually dp dz if it is linear. Clear? So in this way also we can establish that why this we can write as a linear form. So, but it may not be linear. It may not be linear if you are having other loss terms involved. Okay. তখন কিন্তু লিনিয়ার নাও থাকতে পারে। Particularly এই কেসে straight parallel pipe, in such situation we can write in this manner. ঠিক আছে? Otherwise you need to know the correct form of dpdz and then you write in that way. Okay. পরিষ্কার না গন্ডগোল আছে?
Sir, in case of other losses also, if they are there, we will always be here, sir, with respect to Z.
If it is steady, I know. If it is steady, again, those will become linear. Correct.
Because sir, the other losses do not have anything to do with L. They only have the parameter consideration. The other losses like sudden expansion, sudden contraction, they have nothing to do with the L factor.
Yeah, that is actually KQ square. Now, if you are having a steady flow, it is other losses we express in general as KQ square, correct? But K varies. K for bend, K for expansion, K for contraction. The value of this coefficient K attached with Q, that actually varies. So for that situation also, if you are having Q constant, Q steady, so that is why I have added this term steady. For steady state, it doesn't matter. Again, it will be constant. Isn't it?
Yes, sir.
It is. If it is unsteady state, then the things will be different. Okay, so that is not our right now. That is not our purview to consider. So this is why we and mathematically, as previously as we have seen, that rightly pointed out. I mean, from these also you can infer that dpdz should be linear or constant. P is a linear variable of z. That also you can infer directly from that mathematical expression. Okay. So this is the way actually you need to look into the situation. So for the rest two situations, I mean, the basic approach remains same. The basic approach remains same. So if you go through those, I think you can able to grasp what actually we have tried to do. It is basically the different situation. Here, as you can see on your screen, it is a case of two concentric rotating cylinders separated by a fluid of certain viscosity. So here it is not the axial flow, but rather the flow is being driven. It is a kind of, you can say, wet flow for two concentric cylinders, right? The two surfaces are not flat as it was in case of wet flow. It is a curved surface. It's two cylindrical surfaces. and they are having two different motion. One is rotating at omega 1 and the other is rotating at omega 2. So for that, I mean, the fluid in between, typically these type of situations arises in case of bearing, I mean, which actually are being used to have the motion of a shaft and also to support the system. So one will be rotating, the other will be fixed, and the thrust is being supported by the hydraulic fluid. It is separated, the two elements are being separated by a very small distance in the order of less than a millimeter. And that is why actually the flow in between those two surfaces can be considered to be laminar. And that is the main application of this viscous incompressible flow, you can say. And as it is hydraulic, I mean oil as the medium, so you can fairly consider that to be incompressible if there is not much change in temperature. Under that situation, I mean, these treatments are being done to find out what actually the torque is being required to rotate one with respect to other. So thereby, what is the power required? I mean, the bearing friction actually is needed to evaluate so that one can understand what amount of power will be consumed to overcome that friction. Okay. So here in this particular situation, we went up to the evaluation of the torque, which for the earlier cases were not there. We remained up to finding out the discharge of the flow rate. Here, if you look towards the end, we tried to obtain the shear stress and thereby the torque. Okay, it's T1 and T2, the two different torque, and actually both are same. We have obtained like that. And in the last case, it was again the two concentric cylinders which are not rotating, and a flow is occurring through the annulus. Okay, which is in axial direction. So it is again the two concentric cylinders, but those are not rotating. So two non-rotating concentric cylinders. And the space is separate. I mean, filled with viscous liquid fluid, and it is having a motion which is axial.
So এটাতে না ওই শিয়ার স্ট্রেসের ইয়েটা একটু ভুল আছে, শিয়ার স্ট্রেসের ওই এক্সপ্রেশনটা একটু ভুল আছে, মানে ডিআউ ডিআর ডেল আর হবে আর কি।
হতে পারে ভুল, কোনখানটা বলবো?
ওর নিচের পাতাটা, ওর পরের পাতাটা। আচ্ছা ওই আপনার ওই ডিফারেন্সিয়াল কন্ট্রোল ভলিউমটা, হ্যাঁ ওইখানটা,
এইখানে হ্যাঁ কোথায় ভুলে যাবো?
ওই যে ডি টাউ, এই টাউ প্লাস ডি টাউ ডিজেড
ডি না, এটা ডেল টাউ। This you should spell it correctly. This pronounce it as del. It is a partial differential, not d. Del tau, del z, delta z. এটা ভুল আছে বলছো?
ডেল জেড, হ্যাঁ স্যার ওটা হবে ডেল টাউ ডেল আর ডেল্টা আর খুব সম্ভবত।
আচ্ছা, তার মানে তার পরের এই ইকুয়েশনটা লেখাতেও ভুল থাকছে, তাই না?
হ্যাঁ ওখানে থাকছে, কিন্তু ওই 3 নম্বর লাইন থেকে আপনি ঠিকই আছে।
ঠিক আছে, তারপর না ওটা একটু কাটাকাটি হয়ে যাও করে একটা কিছু ঠিক হয়ে গেছে। ঠিক আছে, ওকে, থ্যাংক ইউ ফর পয়েন্টিং আউট, আই শুড কারেক্ট ইট। এইটা তুমি বলছো যেটা এটা ডেল্টা ও ডেলার, হ্যাঁ ঠিকই, কারণ এটা তো আমার গ্রেডিয়েন্ট অ্যাকচুয়ালি আর ডাইরেকশনে, গ্রেডিয়েন্টটা আর ডাইরেকশনে, এটা তুমি বলছো আর হবে, এটা ডেল্টা আর। আচ্ছা, ঠিক 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 ঠিক। And accordingly, I need to change this expression as well, right? Take the word, sir.
Yes, sir.
Yes, yes. Okay, so thank you. So you have gone through it meticulously. That's why you have pointed out this thing. Thank you. I will correct it, and the corrected version we post it in the classroom. Okay. তো এইভাবে জিনিসটা these are the treatment that has been done, and then and that is it actually for the viscous incompressible flow. Already we have posted the sample problem set. So you start doing that. You start attempting to solve. We will be having a discussion on this problem solving part, but again, it should not be like that. Starting from problem number 1 to the end, all problems are going to be discussed. Okay, you should give the feedback that you have done these and these problems. Most of the problems are having their answers. Answers may be wrong also. So I'm not claiming that everything is correct. So, but answers are given. Okay, in most of the problems, one or two problems might have no answers. So you should go through it and let us take 1 week time. In the next week, we will move into the potential flow theory. If you do not have any more query or clarification required regarding the theory part of this viscous incompressible flow, we can straight away move into the potential flow, and for that the required material also we will post it in the classroom by today or latest by tomorrow, so that you can get time to go through it. Okay. And I think potential flow we need more than a week time, because it is content wise it is more than viscous incompressible flow. Okay. Somebody was trying to enter anyway. So I think that's it for today. And thank you very much for your attention. So I am stopping the recording, and also let us conclude the class for today. Okay.
Thank you, sir.